Hi everyone, welcome to this video on an introduction to mathematical proofs. If you're new to my channel, I post tutorials covering key maths topics to help with studying and revision. And today's tutorial will hopefully share some basics of how to approach questions on mathematical proofs. We need to use mathematical facts, techniques, and logic to work towards the solution, because the answers are not numerical. I've listed here some of the main approaches used with mathematical proofs. There are others, but perhaps some of the most commonly used methods are listed. So starting with proof by deduction or direct proof, where we use mathematical facts to construct an argument to show that a statement must be true or false. Then proof by counterexample, and this involves just finding one example that shows that a mathematical statement is false. We then have proof by exhaustion, otherwise known as proof by cases. This is similar to proof by deduction, but the key technique in the proof is that we need to break down the proof into two or more cases and then prove each case individually. There is also proof by contradiction, where we assume that the statement to be proved is not true, and then show that something impossible would have to be true in order for the statement to not be true. And finally, we have proof by induction, which is used to prove that a statement is true for all natural numbers. There's quite a few techniques on here. So in this tutorial, I'm going to focus on the first three. And then I will create a part 2 tutorial to cover examples using proof by contradiction and proof by induction. So starting with direct proofs. Firstly, we need to note some key concepts that will help us to construct our arguments for direct proofs. Firstly, any even number can be written as 2n, and that intuitively makes sense. We can write 2 as 2 times 1, 4 as 2 times 2, 6 is 2 times 3, and so on. Thus, any odd number can be written as 2n plus 1, because we know that in a sequence of natural numbers, we have odd, even, odd, even, odd, even. Therefore, if any even number is 2n, an odd number will be the number that follows the even number. Consecutive numbers can be written as n, n plus 1, n plus 2. And all of these statements are true where n is an integer. So starting with an example, prove that the sum of any three odd numbers is also odd. We can write three odd numbers as 2x plus 1, 2y plus 1, and 2z plus 1. And we use the notation x, y, and z just to show that we are talking about three different odd numbers. We can then write an expression adding them together, which we can then rearrange to give 2x plus 2y plus 2z plus 2 plus 1. And the key thing to note here is writing the constant at the end of the equation in the format plus 2 plus 1, because this allows us to then rearrange in the format 2 brackets x plus y plus z plus 1 plus 1. And that means we have presented the result in the format 2n plus 1, where n is the integer x plus y plus z plus 1. And thus, we have shown that the sum of any three odd numbers is odd. Let's try another example of a direct proof. So here, we're asked to prove that the difference between the squares of two consecutive even numbers is always a multiple of 4. As before, perhaps the most difficult part of the proof is where to start, and here it's defining two consecutive even numbers. Well, we know that an even number we always write as 2n, And if we want two consecutive even numbers, we need 2n and 2n plus 2. We wouldn't, of course, have 2n plus 1 because that would be the odd number in between. Thus, the difference in squares of two consecutive even numbers can be expressed as 2n plus 2 squared minus 2n squared. We can then expand out of the brackets, and this gives us 4n squared plus 8n plus 4 minus 4n squared. And this simplifies to 8n plus 4, which we can then factorize and have 4 outside the bracket and 2n plus 1. Thus, the resulting number can always be divided by 4 to give 2n plus 1 for any integer n. Therefore, we have proved that the difference between the squares of two consecutive even numbers is always a multiple of 4. And actually, in this example, the multiple of 4 will be an odd number because we have 2n plus 1 inside the brackets. One of the nice things about a number of proofs is you can actually test the proof. So let's do this here. If we take n to be the integer 5, then the two consecutive numbers that we are considering are 10 and 12. So we substitute these in. 12 squared is 144, less 10 squared, which is 100. This gives a difference of 44, which divides by 4 to give the odd number 11. So we have shown or used numbers to check that our proof is correct. Going through another direct proof example then, this time something slightly different. So we're presented with a flow process or a number machine that takes an input x, multiplies it by a, b is then added, and y is the output. And here I think we can assume that all of these numbers are integers. So the question asks us to prove that if the input increases by 2, the output increases by 2a. So firstly, we need to write this as equations. Our initial input then, which we can call y1, is ax plus b. And then to get our new input and output, we are increasing the input by 2, so x becomes x plus 2, which we can substitute in, and we can call the output y2. So here we have y2 equals ax plus 2a plus b. And then we want to show how the output has increased, so we can calculate the variance. So y2 subtract y1, and this gives us 2a. And thus we have proved that the increase in output is 2a. Sometimes with questions on proofs, you can perhaps misinterpret. So I firstly would have maybe read this as input increases by 2, as in the input is doubling, at which point I would have substituted 2x. But then working through the proof, the answer would not have been 2a. And so I would check and try and make sure I fully understand the question, and then realize that here it's asking for x plus 2. So I think that's, again, a nice thing with proofs. You can kind of tell if you're on the right track or not. Let's now use the direct proof method to prove that a statement is false. Our previous examples have all been about proving that a statement is true, but equally you can use this approach to prove something is false. So here we have a question where we're told that the function of x is kx squared and k is a constant. Tim says that f of 6 divided by f of 2 is equal to f of 3 because 6 divided by 2 is 3. Is he correct? Show a working to support your answer. Well, firstly, we take the left-hand side. And here we can put these numbers into the function. So we have 36k divided by 4k, which is 9. And then take the right-hand side, so the function of 3 is equal to 9k. Well, then 9 would not equal 9k whenever it's the case that k does not equal 1. So no, Tim is not correct. And again, if we want to verify this, we can test our proof again. Suppose k is equal to 3, but you could use any number that's not 1. Then f of 6 divided by f of 2 gives 9, as before. But when we put 3 into the function, we get an output of 27. And 27 is not equal to 9. Another way of proving a statement is false is proof by counterexample. So here we have an example asking us to disprove the following. If w is smaller than x, is less than y, is less than z, and x and z are not equal to 0, then the fractions of w over x must be less than y over z. As we're doing proof by counterexample, rather than using mathematical facts to construct an argument, we can instead just find one example and use example numbers, which is the approach taken here. So let w be equal to 1, x be equal to 2, y equal to 3, and z equal to 10. We can use any numbers, any set of numbers, as long as we follow the first part above. So w has to be less than x, etc. Then we can create the fractions. So w over x would be a half, and y over z equals 3/10. But 1/2 is greater than 3/10. It's not less than 3/10. And so the statement above is not true. The third type of proof that we're going to run through today is proof by exhaustion. And this is where we need to break our proof down into scenarios and then work through each case individually. Taking an example, here we're asked to prove that for any integer x, the value of the function f of x, x cubed plus 3x plus 5, is an odd integer. This then is not too different from the techniques that we use when we're solving for direct proofs, but it has an additional step in that we need to identify the individual cases. So as we're being asked to prove the statement for any integer x, in this example, our two cases would be where x is an even integer and where x is an odd integer. So if we start with scenario 1, where we assume that x is an even integer, as before, this can be expressed as x equals 2n for some integer n, and we can substitute 2n into our function, which gives us 8n cubed plus 6n plus 5. We can rearrange this, and we know from before that if n is an integer, then 2 times 4n cubed plus 3n plus 2 plus 1 is an odd integer. We then use the same approach, but this time we start by assuming that x is an odd integer. If x is odd, it can be expressed as x equal to 2n plus 1 for some integer m. So we substitute 2n plus 1 into the function, and we rearrange, and we show that this gives us 2 times, all in brackets, 4m cubed plus 6m squared plus 5m plus 4. But we have a plus 1 at the end. The output is an odd integer. And because we have shown that f of x gives us an odd number when x is even and when x is odd, we have therefore proved that the function of x is odd for any integer x. So just summarizing what we've covered today, we've started with outlining the key types of mathematical proofs. We have then looked at examples of proof by deduction, otherwise known as direct proofs. We've seen an example of a proof by counterexample, and then we've looked at proof by exhaustion. In part two, I will talk through some examples of proof by contradiction and proof by induction. But I hope that you found this tutorial useful to give an idea of how to start with initial mathematical proofs. I hope you liked this video. If you did, please give it a thumbs up. Also, if you have any requests for content for future tutorials, please let me know and I will prioritize that. Thanks for watching.